This presentation has three elements. There's the basic texture attributes as implemented in OpendTect. And then there is a second group of attributes which are called directional texture attributes, also implemented in the free version of OpendTect. And these were developed by Geo5, a partner of DGB. And Geo5 is a spin-off of Joanneum Research Institute in Austria. These directional attributes, these directional texture attributes, are the input again to FracTex, and FracTex is a commercial plugin by Geo5. Now, what are texture attributes? It's really already quite old. They have been around since the 1970s. It comes from image processing and is based on Haralick's description of gray level co-occurrence matrix. These attributes describe the roughness and smoothness of an image, and what a gray level co-occurrence matrix is I will describe in my next slide. In seismic interpretation, it has been used for many years for seismic facies interpretation and also to highlight geomorphological features, and it's still used today. It's a very valuable interpretation technology attribute. Just today, it's March 2025, in First Break, the latest issue, I saw a presentation in which GLCM attributes were used. So, how do we construct a gray level co-occurrence matrix? Let's look at this image, and the values are the gray levels here. So we have pixels of 0 gray and 1, 2 and 3 gray levels. Now, each of these cells we can identify in this matrix. So this is the cell with position 0, 0, then we have 0, 1, 0, 2, and so on. What we're going to do is we're going to count how many neighbors we have of 0 to 0. And this will be mapped in the matrix in this cell. So this is one occurrence of 0 next to 0. This is another one, 0 to 0. But then we also have these two cells from 0 on the other side to 0 and this one. So in total we have 4 occurrences of 0 next to 0 in this particular image. Now we can normalize that to probabilities on how many occurrences do we have in total in this image. And then we fill in the matrix as follows. We just count everything, convert it to probabilities, and that is our GLCM matrix. From that GLCM matrix we compute attributes. And we do that in 3 different groups. One group is called the contrast group, and these are measurements based on the distance from the GLCM diagonal. And the first attribute in this contrast group is called contrast. And this is an example. Input on the left, and let me get my slide pointer again, laser pointer. So input here and attribute on the right. Contrast, dissimilarity belongs to the contrast group. Homogeneity. And then we come into the next group, and that is called the orderliness group. And these are measurements of how organized the GLCM matrix itself is. This particular attribute is called the angular second moment. This one is the energy, and this one is the entropy. All part of the orderliness group. Now then the third group we have is just statistical measurements. So on the right we see the GLCM mean, the GLCM variance, the GLCM standard deviation, and GLCM correlation. All these attributes that I've shown here are available in a group in the attribute engine under the texture attributes. Now, all these attributes can be dip-steered, and dip-steered is a typical thing in OpendTect, whereby we use a plugin to calculate the dip field. We call that output the steering cube, and the steering cube has 2 components. It has the inline dip and the crossline dip. And we can use that dip to create small virtual horizons at every position just by following the dip outwards. And then we can extract the information we want along the dip, that structural reflection system. So let's have a look how that works. This is the dip field, the calculated dip. We're looking here at dips dipping in this direction, colored in red, and dips going to the other direction in blue, and in between we have white and yellow colors. Now, if I would extract a multi-trace attribute from this central position, I can go traces outwards and I can trace samples upwards and downwards, and I can do that in a certain circle or a certain cube in 3 dimensions and extract the information. If I don't use any dip steering, this is how the information would be extracted, just horizontally and vertically. And then I compute my attribute. If I use dip steering, I'm starting from here, I look at the dip at this location and I'm following that dip to find the next cell. And then from here I can find the next cell using that dip and so on. So I can really follow the seismic reflector everywhere. If I put this input into an attribute, I get a response that really belongs to the geologic information that we are following. And here we see an example of that effect, of the effect of dip steering on a GLCM attribute, in this case correlation. On the left we see non-dip steered GLCM correlation, and on the right we see dip steered. Here we see that the attribute is really following our seismic reflections, so we get a response pertaining to the geologic information and not just cross-cutting all these different layers. So dip steered is always giving you a better response, that's the message. Now let's look at directional attributes. So that is something that was computed by or developed by Geo5, and it's available in the free version of OpendTect. Each cell, in this case the middle cell here, has 26 neighbors, and that allows for computations in 13 different directions. So I can, from this cell, go into the inline direction and just compare what is next to these cell information. I can go into the crossline direction, I can go vertical, but I can also going from this cell to that cell and up there in a certain direction. So that gives 13 different ways to analyze the information in all these different directions. If we do that for texture analysis, let's look at this gray image, just a synthetic gray image, and here are the gray levels in this particular gray image, scale image. And what we're going to do is we're going to compute different attributes for this image in different directions. So first we're going to compute the GLCM matrix just in the horizontal direction, and that gives you this matrix from which we can compute the GLCM energy, contrast, homogeneity, entropy, cluster tendency, and you get these values. Now the next thing we're doing, we're going to repeat it, but now we're going to compute it in this direction. And we get different values here for the attribute responses. Similarly here in this direction, different responses as compared to this direction, as compared to doing it in all directions. Now what have we learned from this analysis? That if we would compute it in this direction, the horizontal direction, then all the attribute values tend to be average for this particular image. If we go in the vertical direction, we find the highest cluster tendency. In this direction we find the highest contrast and the lowest homogeneity. In this direction, lowest energy, lowest cluster tendency, and in all directions the highest entropy. An example in 2D, this is a interpreted horizon, and we see channels in this system. This is in the Vienna Basin, this is coherency, and this is the interpretation. We're going to compute different GLCM attributes, energy, homogeneity, and so on. And we find this one, the energy, the most interesting because it tends to pick up the channels best compared to the other attributes. So now we're going to analyze this in different directions, and what we see is that some of these channels are picked up in different directions. They're brightening in different directions. So there is an anisotropy in this image. And what can we learn from all this? First of all, that texture attributes are valuable tools in seismic interpretation. That has been for the last 50 years or so, and it's still valuable today. Original applications are for seismic Facies analysis and visualization of geomorphological features. The dip steering constrains the analysis to stratigraphic layering and generates higher signal-to-noise ratios and better responses for texture attributes. Directional analysis reveals anisotropy in the image, and now we come to the FracTex. So dip-steered directional texture attributes have potential for analyzing anisotropy and rock properties and can thus be used in the analysis of fracture density, stress fields, fluid flow and paths, and that is where FracTex comes in. So FracTex, it computes directional variations of these GLCM attributes, and that is done mainly for fracture analysis. There are two basic outputs from FracTex. One is the anisotropy, so that is a factor which ranges from 1 to higher, and the higher it is, the more anisotropic the medium is. 1 means the medium is isotropic. And fracture dip azimuth, that is the azimuth in which we have the largest variability in variations in GLCM attribute response.